Yes, welcome back. Let's try read this one, but the power is kind of low. But let's get started.
Semiconductor device fabrication. NASA's Glenn Research Center clean room external image icon. Photo of the interior of a clean room of a 300mm fab run by TSMC. Semiconductor device fabrication is the process used to manufacture semiconductor devices, typically integrated circuit, IC, chips such as modern computer processors, microcontrollers, and memory chips such as NAND flash and DRAM that are present in everyday electrical and electronic devices. It is a multiple-step sequence of photolithographic and chemical processing steps, such as surface passivation, thermal oxidation, planar diffusion and junction isolation, during which electronic circuits are gradually created on a wafer made of pure semiconducting material. Silicon is almost always used, but various compound semiconductors are reused for specialized applications. The entire manufacturing process takes time, from start to packaged chips ready for shipment, at least 6 to 8 weeks. Tape out only, not including the circuit design, and is performed in highly specialized semiconductor fabrication plants, also called foundries or fabs. 1. All fabrication takes place inside a clean room, which is the central part of a fab. In more advanced semiconductor devices, such as modern 14/10/7 nodes, fabrication can take up to 15 weeks. With 11-13 weeks being the industry average. 2. Production in advanced fabrication facilities is completely automated and carried out in a hermetically sealed nitrogen environment to improve yield. The percent of microchips that function correctly in a wafer, with automated material handling systems taking care of the transport of wafers from machine to machine. Wafers are transported inside FOUPs, special sealed plastic boxes. All machinery and FOUPs contain an internal nitrogen atmosphere. The air inside the machinery and FOUPs is usually kept cleaner than the surrounding air in the clean room. This internal atmosphere is known as a mini-environment. 3. Fabrication plants need large amounts of liquid nitrogen to maintain the atmosphere inside production machinery and FOUPs, which is constantly purged with nitrogen. 4. Contents. Size. History 20th century. 21st century. List of steps. Prevention of contamination and defects. Wafers. Processing front end of line, fill, processing gate oxide and implants. Back end of line, bill, processing. Metal layers. Interconnect. Wafer test. Device test. Device yield. Die preparation. Packaging. Hazardous materials. Timeline of commercial MOSFET nodes. See also. References. Further reading. External links. Size. A specific semiconductor process has specific rules on the minimum size and spacing for features on each layer of the chip. 5. Often a newer semiconductor processes has smaller minimum sizes and tighter spacing which allow a simple die shrink to reduce costs and improve performance. 5. Partly due to an increase in transistor density, number of transistors per square millimeter. Early semiconductor processes had arbitrary names such as MOS3, CMOS-V. Later ones are referred to by size such as 90 nm process. By industry standard, each generation of the semiconductor manufacturing process, also known as technology node 6 or process node 7, 8, is designated by the process's minimum feature size. Technology nodes, also known as process technologies or simply nodes, are typically indicated by these I's in nanometers, or historically micrometers. of the process transistor gate length. However, this has not been the case since 1994. Initially, transistor gate length was smaller than that suggested by the process node name, for example 350 nm node. However, this trend reversed in 2009. 9. The nanometers used to name process nodes has become more of a marketing term that has no relation with actual feature sizes nor transistor density, number of transistors per square millimeter. For example, Intel's former 10 nm process actually has features. The tips of FinFET fins, with a width of 7 nm. Intel's former 10 nm process is similar in transistor density to TSMC's 7 nm processes, while Global Foundries 12 and 14 nm processes have similar feature sizes. 10, 11, 12. History. 20th century. An improved type of MOSFET technology, CMOS, was developed by Chitang Sa and Frank von Lass at Fairchild Semiconductor in 1963. 13, 14. CMOS was commercialized by RCA in the late 1960s. 13. RCA commercially used CMOS for its 4000 series integrated circuits in 1968. Starting with a 20 process before gradually scaling to a 10 micrometers process over the next several years. 15. Semiconductor device manufacturing has since spread from Texas and California in the 1960s to the rest of the world, including Asia, Europe, and the Middle East. 21st century. The semiconductor industry is a global business today. The leading semiconductor manufacturers typically have facilities all over the world. Samsung Electronics, the world's largest manufacturer of semiconductors, has facilities in South Korea and the US. Intel, the second largest manufacturer, has facilities in Europe and Asia as well as the US. TSMC, the world's largest pure-play foundry, has facilities in Taiwan, China, Singapore, and the US. Qualcomm and Broadcom are among the biggest fabless semiconductor companies, outsourcing their production to companies like TSMC. 16. They also have facilities spread in different countries. Since 2009, Node has become a commercial name for marketing purposes that indicates new generations of process technologies, without any relation to gate length, metal pitch or gate pitch. 17, 18, 19. For example, Global Foundries 7 nm process is similar to Intel's 10 nm process, thus the conventional notion of a process node has become blurred. 20. Additionally, TSMC and Samsung's 10 nm processes are only slightly denser than Intel's 14 nm in transistor density. They are actually much closer to Intel's 14 process than they are to Intel's 10 nm process. For example, Samsung's 10 nm process's fin pitch is the exact same as that of Intel's 14 nm process, 42 nm. 21, 22. As of 2019, 14 nanometer and 10 nanometer chips are in mass production by Intel, UMC, TSMC, Samsung, Micron, SK Hynix, Toshiba Memory and Global Foundries, with 7 nanometer process chips in mass production by TSMC and Samsung, although their 7 nanometer node definition is similar to Intel's 10 nanometer process. The 5 nanometer process began being produced by Samsung in 2018. 23. As of 2019, the node with the highest transistor density is TSMC's 5 nanometer N5 node. 24, with a density of 171.3 million transistors per square millimeter. 25. In 2019, Samsung and TSMC announced plans to produce 3 nanometer nodes. Global Foundries has decided to stop the development of new nodes beyond 12 nanometers in order to save resources. as it has determined that setting up a new fab to handle sub-12 nm orders would be beyond the company's financial abilities. 26. As of 2019, Samsung is the industry leader in advanced semiconductor scaling, followed by TSMC and then Intel. 27. List of steps. This is a list of processing techniques that are employed numerous times throughout the construction of a modern electronic device. This list does not necessarily imply a specific order. Equipment for carrying out these processes is made by a handful of companies. All equipment needs to be tested before a semiconductor fabrication plant is started. 28. These processes are done after integrated circuit design. Wafer processing, wet cleaning by solvents such as acetone, trichloroethylene and ultrapure water. Piranha solution. RCA clean. Surface passivation. Photolithography. Ion implantation, in which dopants are embedded in the wafer creating regions of increased or decreased conductivity. Etching, microfabrication, dry etching, plasma etching, reactive ion etching, RIE, deep reactive ion etching. Atomic layer etching, ALE. Wet etching, buffered oxide etch. Plasma ashing. Thermal treatments, rapid thermal anneal. Furnace anneals. Thermal oxidation. Chemical vapor deposition, CVD. Atomic layer deposition, ALD. Physical vapor deposition, PVD. Molecular beam epitaxy, MBE. Laser liftoff, for lead production, 29. Electrochemical deposition, ECD. C. Electroplating. Chemical mechanical polishing, CMP. Wafer testing, where the electrical performance is verified using automatic test equipment. Binning and forward/or laser trimming may also be carried out at this step. Die preparation through silicon via manufacture, for three-dimensional integrated circuits. Wafer mounting. Wafer is mounted onto a metal frame using dicing tape. Wafer back grinding and polishing, 30, reduces the thickness of the wafer for thin devices like a smart card or PCMCIA card, or wafer bonding and stacking. This can also occur during wafer dicing, in a process known as dice before grind or DBG, 31, 32. Wafer bonding and stacking, for three-dimensional integrated circuits and MEMS. Redistribution layer manufacture, for WLCSP packages. Wafer bumping, for flip chip BGA, ball grid array, and WLCSP packages. Die cutting or wafer dicing. IC packaging, die attachment. The die is attached to a lead frame using conductive paste or die attach film, 33, 34. IC bonding, wire bonding, thermosnic bonding, flip chip or tape automated bonding, tab. IC encapsulation or integrated heat spreader, IHS, installation molding, using special molding compound that may contain glass powder as filler. Baking. Electroplating, plates the copper leads of the lead frames with tin to make solder angiosia. Laser marking or silk screen printing. Trim and form, separates the lead frames from each other, and bends the lead frames pins so that they can be mounted on a printed circuit board. IC testing. Additionally, steps such as right edge may be carried out. Progress of miniaturization, and comparison of sizes of semiconductor manufacturing process nodes with some microscopic objects and visible light wavelengths. Prevention of contamination and defects. When feature widths were far greater than about 10 micrometers, semiconductor purity was not as big of an issue as it is today in device manufacturing. As devices become more integrated, clean rooms must become even cleaner. Today, fabrication plants are pressurized with filtered air to remove even the smallest particles, which could come to rest on the wafers and contribute to defects. The ceilings of semiconductor clean rooms have fan filter units, FFUs, at regular intervals to constantly replace and filter the air in the clean room. Semiconductor capital equipment may also have their own FFUs. The FFUs, combined with raised floors with grills, help ensure laminar airflow, to ensure that particles are immediately brought down to the floor and do not stay suspended in the air due to turbulence. The workers in a semiconductor fabrication facility are required to wear clean room suits to protect devices from human contamination. To prevent oxidation and to increase yield, FOUPs and semiconductor capital equipment may have a hermetically sealed pure nitrogen environment with ISO Class 1 level of dust. FOUPs and Smith pods isolate the wafers from the air in the clean room, increasing yield because they reduce the number of defects caused by dust particles. Also, fabs shave as few people as possible in the clean room to make maintaining the clean room environment easier since people, even when wearing clean room suits, shed large amounts of particles, especially when walking. 35, 36, 37 wafers. A typical wafer is made out of extremely pure silicon that is grown into monocrystalline cylindrical ingots, up to 300 millimeters, slightly less than 12 inches, in diameter using the Czochralski process. These ingots are then sliced into wafers about 0.75 millimeters thick and polished to obtain a very regular and flat surface. Processing. In semiconductor device fabrication, the various processing steps fall into 4 general categories: deposition, removal, patterning, and modification of electrical properties. Deposition is any process that grows, coats, or otherwise transfers a material onto the wafer. Available technologies include physical vapor deposition, PVD, chemical vapor deposition, CVD, electrochemical deposition, ECD, molecular beam epitaxy, MBE, and more recently, atomic layer deposition, ALD, among others. Deposition can be understood to include oxide layer formation by thermal oxidation or, more specifically, locus. Removal is any process that removes material from the wafer. Examples include etch processes, either wet or dry, and chemical mechanical planarization, CMP. Patterning is the shaping or altering of deposited materials, and is generally referred to as lithography. For example, in conventional lithography, the wafer is coated with a chemical called a photoresist. Then, a machine called a stepper focuses, aligns, and moves a mask exposing select portions of the wafer below to short wavelength light. The exposed regions are washed away by a developer solution. After etching or other processing, the remaining photoresist is removed by dry plasma ashing, photoresist stripping or strip. The photoresist may also be removed using wet chemical processes that coat the wafer in a liquid to remove the photoresist. 38. Modification of electrical properties has historically entailed doping transistor sources and drains, originally by diffusion furnaces and later by ion implantation. These doping processes are followed by furnace annealing or, in advanced devices, by rapid thermal annealing, RTA. Annealing serves to activate the implanted dopants. Modification of electrical properties now also extends to the reduction of a material's dielectric constant in low-K insulators via exposure to ultraviolet light in UV processing, UVP. Modification is frequently achieved by oxidation, which can be carried out to create semiconductor insulator junctions, such as in the local oxidation of silicon, locus, to fabricate metal oxide field effect transistors. Modern chips have up to 11 or more metal levels produced in over 300 or more sequenced processing steps.
Yes, the video is too long. Let's stop the video and use my old Canon camcorder for the video splits.